If you haven't already heard, our very own solar system is currently playing host to an extraordinary and truly captivating visitor. This celestial enigma, Comet 3I/Atlas, dramatically burst onto the astronomical scene in early July of 2025. Its initial identification came courtesy of the NASA-funded Atlas Survey Telescope, an acronym for the Asteroid Terrestrial Impact Blast Alert System, diligently operating from its vantage point in Rio Hurtado, Chile. Since that pivotal moment, scientists from every corner of the globe have coalesced, driven by a shared urgency to glean every conceivable scrap of information about this elusive entity. This intense scientific spotlight has naturally ignited a veritable flurry of articles, urgent alerts, peer-reviewed papers, and even heated controversies surrounding what has been confirmed as the first interstellar object to venture into our cosmic backyard in a remarkable 6 years. But amidst this swirling media frenzy, this whirlwind of information and speculation, what substantive knowledge have we truly acquired? How do we discern what facts about this comet are empirically true, and what tantalizing narratives perhaps wander into the imaginative realms of science fiction? I'm Alex McColgan, and you're currently tuned into Astro. Join me in this video as I endeavor to provide you with a much-needed, distilled update on 3I/Atlas, meticulously piercing through the often conflicting noise of conjecture and speculation to get right to the heart of what fundamentally makes this transient visitor so profoundly special. If nothing else, the sheer magnitude of the buzz and excitement surrounding this comet serves as a potent testament to just how dynamic, unpredictable, and endlessly fascinating the world of scientific research can truly be. Consider this. When I produced my inaugural video about 3I/Atlas back in July, the scientific literature boasted a mere handful, roughly 4, published research papers even mentioning its name. Fast forward to today, and that number has exploded to nearly 70. This exponential growth isn't just a statistic. It represents a monumental surge in new discoveries, rigorous verifications of existing data,
Hubble's
and
data
ultimately,
provided the
a
clarity
profound
we needed.
boost in our collective, ever-evolving knowledge base concerning this enigmatic object. It's a clear indicator of a scientific community galvanized into action, working in concert. Before we dive headfirst into the very newest and most groundbreaking findings, let's take a moment for a swift, yet essential, recap of where we last left off. In my previous video, we thoroughly discussed the initial, thrilling discovery of Comet 3I/Atlas, a name laden with significance, denoting its status as the third confirmed interstellar object to gracefully traverse our solar system. We also touched upon the Atlas Survey Telescope, the vigilant eye that first identified it, tirelessly scanning the night sky for unexpected anomalies. I drew illuminating comparisons between 3I/Atlas and its famed predecessors, Oumuamua, that peculiar, cigar-shaped visitor which captivated the world as it made its perplexing journey through our solar system in 2017, and Borisov, the more comet-like interstellar traveler discovered in 2019. In stark contrast to both of these earlier interstellar trailblazers, 3I/Atlas is now understood to be significantly faster, hurtling through the vacuum of space at a mind-boggling speed of 58 kilometers per second. Imagine something moving roughly 130,000 miles per hour. Furthermore, it's estimated to be considerably older, with age assessments placing its genesis somewhere between a staggering 3 and 11 billion years ago, making it an ancient wanderer indeed. That, admittedly, was a whirlwind summary, so I strongly encourage you to explore my first video for a more exhaustive and in-depth exploration of those foundational details. However, since 3I/Atlas made its grand debut on our channel, our understanding of it has expanded exponentially, all thanks to countless dedicated hours of meticulous observation and precise measurements painstakingly gathered from an extensive network of advanced astronomy facilities spanning the entire globe. So, with this intensified researching spree, what truly is the very latest, cutting-edge information to emerge? Given the immense, worldwide recognition that 3I/Atlas has effortlessly commanded since its initial discovery, it has undeniably succeeded in turning the venerable heads of two of the most prestigious and powerful telescopes known to humanity. It is famously, almost notoriously, difficult to secure observation time with NASA's iconic Hubble Space Telescope. Scientists routinely dedicate months, sometimes even years, to crafting intricate proposals, fiercely arguing their case for every precious minute of the telescope's invaluable operational time. Yet, in a stroke of cosmic luck for 3I/Atlas, Hubble always wisely reserves a small, critical allocation of time for what are termed targets of opportunity. These are fleeting celestial phenomena that simply must be observed before they slip irrevocably out of our reach. This special designation effectively granted our unexpected interstellar visitor a golden free pass, allowing it to elegantly skip the notoriously long queue. And, as the subsequent data unequivocally revealed, it was an allocation of time that proved to be immeasurably worthwhile. Hubble successfully captured this stunning image of 3I/Atlas when it was still an immense 446 million kilometers, approximately 277 million miles, distant from Earth. Even in that image, you can vividly perceive the comet's breathtaking velocity from the subtly streaky appearance of the background stars, a visual artifact caused by Hubble precisely tracking the rapidly moving comet, giving the fixed stars a blurred effect. More strikingly, the image clearly reveals the distinct, teardrop-like shape of the dust and gas gracefully streaming off its icy nucleus, painting a dynamic portrait of its ongoing transformation. These invaluable observations also empowered Hubble scientists to refine their estimates for the actual size of 3I/Atlas's nucleus, now placing its diameter somewhere between a colossal 440 meters and a sprawling 5.6 kilometers. This new, more precise measurement indicates that the nucleus is considerably smaller than initial estimates had suggested. The initial figures, it turns out, were based on the assumption that the comet's entire reflectance, its apparent brightness, originated solely from its compact nucleus, rather than factoring in the extensive, glowing halo of dust and gas, known as the coma, surrounding it. But now that the dust has cleared, so to speak, in our understanding, we are privileged to view these cosmic phenomena in far finer, more revealing detail. Indeed, future observations hold the promise of further refining and pinning down these critical measurements with even greater precision, peeling back yet more layers of its mystery. The other colossal player that has, perhaps inevitably, turned its incredibly powerful gaze toward 3I/Atlas is none other than the revolutionary James Webb Space Telescope, JWST. Scientists, under the astute leadership of astrochemist Dr. Martin Kortner, deployed JWST's near-infrared spectrograph, a sophisticated instrument capable of dissecting light into its component colors, revealing the unique chemical fingerprints of various molecules. In a concerted effort to definitively ascertain the precise composition of this unprecedented comet, their findings were nothing short of fascinating, revealing a remarkably complex coma morphology, which essentially means the shape and structure of its dusty halo were far from uniform.
Breathtaking.
This complexity strongly suggests a diverse array of outgassing patterns, varying significantly based on the specific elements and compounds being violently released from the nucleus. At this particular stage of its journey, it appeared that carbon monoxide, CO, and carbon dioxide, CO2, were sublimating, transforming directly from solid ice to gas, at a much higher rate than water ice, which is often a dominant volatile in many comets. However, this intriguing imbalance is highly likely to shift dramatically as the comet continues its inexorable journey, drawing ever closer to the intense heat and radiation of the sun. And here's another astonishing twist. While the tails of comets conventionally point away from the sun, propelled by the solar wind and radiation pressure, these researchers unearthed a surprising abundance of dust actively emanating from 3I/Atlas in the direction of the sun. This counterintuitive phenomenon is attributed to incredibly fragile dust grains fragmenting into even smaller pieces as they drift further from the nucleus, subsequently reflecting a greater amount of sunlight. This already remarkable process, scientists theorize, might be further exacerbated by the comet's prolific gas production. Specifically, an excessive outpouring of carbon dioxide could actually be launching these dust particles with greater force, propelling them further away from the nucleus and even, counterintuitively, towards the sun. Quite dramatic, wouldn't you agree, for a feature that, to our distant eyes, often appears as nothing more than a faint, hazy glow in the night sky? The sheer, hidden violence of these processes is truly humbling. But Hubble and James Webb aren't the sole NASA telescopes enthusiastically getting in on the 3I/Atlas fun. The Transiting Exoplanet Survey satellite, affectionately known to astronomers and enthusiasts alike as TESS, has dedicated over 7 years of its mission to meticulously conducting an ambitious all-sky survey. Its primary objective, to relentlessly seek out and discover exoplanets, those alien worlds orbiting around nearby, exceptionally bright stars. TESS accomplishes this colossal task using an array of 4 identical, wide-field cameras, systematically mapping vast swathes of the sky in precisely defined 90 by 24 degree
Global
strips.
synchronization
To
holding
date,
steady
it has
at
already
98%.
successfully
The
identified
chaotic
thousands
signals are
upon
degrading.
thousands of
We
compelling
are
planetary
ready.
candidates. But, as it stunningly turns out, TESS possesses a surprising aptitude not just for pinpointing distant exoplanets, but also for detecting far smaller, more transient objects. Objects, dare we say, like comets. Astronomers diligently working with NASA's TESS mission experienced a truly exciting eureka moment when they realized, in retrospect, that they actually possessed a wealth of observational data for this very comet, dating all the way back to May. Specifically, 3I/Atlas was serendipitously captured by TESS's vigilant cameras from the 7th of May through the 2nd of June, rendered visible only through the careful processing of composite deep stack images, a technique where multiple faint images are stacked together to reveal incredibly dim objects otherwise hidden in the
Astro
cosmic
reports.
background noise. Armed with this newfound treasure trove of earlier data, astronomers were presented with an invaluable opportunity. They could now meticulously verify the initial measurements painstakingly made from 3I/Atlas by other observatories, and, perhaps even more thrillingly, embark on making some entirely new, groundbreaking discoveries of their very own. A dedicated team of researchers, including Adina Feinstein, John Noonan, and Daryl Seligman, seized this opportunity, utilizing the raw data from TESS to precisely measure the intrinsic brightness of 3I/Atlas. Their meticulous analysis revealed that the average visual magnitude, a standard astronomical measure of brightness, recorded by one of the TESS detectors was reassuringly in line with previous estimates already made by other astronomers, even those employing different methods. This consistency served as a powerful validation of their work. However, true to its enigmatic nature, the comet was poised to defy expectations in yet another unexpected way. Between the 7th of May and the 2nd of June, a remarkable celestial alignment saw the distance between the enigmatic interstellar object 3I/Atlas and the keen-eyed TESS spacecraft dramatically shrink by a significant 0.9 astronomical units. To put that into perspective, an astronomical unit, AU, is roughly the average distance from Earth to the Sun, so this represented a substantial close encounter in cosmic terms. Initially, based solely on this tightening proximity, the researchers fully anticipated a noticeable increase in the object's luminosity. After all, a closer proximity to our star, the Sun, naturally means it would be bathed in a greater intensity
The margin of
solar
error is
radiation,
tight, confirming the
inherently
440
capable of
meter to
reflecting more
5.6
of that
kilometer
brilliant
range.
light back
Hubble's
towards
data
us.
provided the
Their
clarity we
meticulous
needed.
calculations projected that the comet's flux, essentially the total amount of energy, specifically light, we receive from it, would intensify by a factor of 1.5. This predicted surge in energy corresponded to an expected apparent magnitude of 20.5, a measure where smaller numbers denote brighter objects. However, what unfolded next sent ripples of excitement through the astronomical community. The object didn't just get brighter, it became dramatically brighter than their conservative predictions. Instead of a mere 20.5 magnitude, its luminosity rocketed to an astonishing 19.28. This wasn't just a small deviation. This shocking, unexpected surge in brilliance revealed that 3I/Atlas had, in fact, boosted its emitted or reflected light energy by an astounding factor of 5, a far cry from the predicted 1.5. What profound forces could be at play to cause such an explosive increase in its radiant energy? Crucially, independent observations from the TRAPPIST North and South telescopes, sophisticated robotic instruments located in opposite hemispheres, providing continuous sky coverage, corroborated these startling brightness values. Their consistent reports eliminated any lingering doubts of a potential miscalculation or observational error. This irrefutable evidence underscored a profound truth. With such an immense quantity of energy now clearly radiating from its surface, 3I/Atlas was unequivocally far more dynamic and volatile than initially conjectured. Indeed, this unprecedented activity hinted at the tantalizing possibility that this interstellar wanderer might have been actively outgassing and releasing material for an extended cosmic period, perhaps even since long before its close approach to the Sun. Further delving into the mysteries, scientists meticulously integrated these newfound magnitude values with previous estimates of 3I/Atlas's nucleus size, painstakingly derived from the venerable Hubble Space Telescope. What they uncovered was truly astounding. Their analysis strongly suggested that 3I/Atlas might have already been robustly active when it was still a staggering 6 astronomical units away from the Sun. To truly grasp the scale of this, consider that $6 places it well beyond the orbit of Mars, deep into the colder, more distant reaches of our solar system, almost brushing against the asteroid belt. This is precisely near the frigid, outer boundaries where most typical comets, composed primarily of water ice, generally begin their first hesitant whispers of outgassing. Could this mean that 3I/Atlas was expelling something far more unusual and exotic, something far more hypervolatile than mere water vapor at such an extreme distance? The data certainly pointed to the potential release of incredibly elusive substances like solid nitrogen or even molecular hydrogen, which sublimate at much lower temperatures, hinting at a truly unique composition and origin story. Recalling a point from a previous discussion, I had noted that 3I/Atlas exhibited a remarkably flatter light curve compared to its notorious predecessor, Oumuamua. This characteristic, flatness, is generally interpreted as the object reflecting sunlight with greater uniformity across its entire surface, suggesting a less irregular or elongated shape, or perhaps a more consistent surface composition. Intriguingly, Dr. Adina Feinstein and her dedicated team of colleagues independently arrived at a strikingly similar conclusion. Their painstaking efforts involved attempting to meticulously extract a detailed light curve for this interstellar visitor, leveraging the rich dataset captured by the Transiting Exoplanets Survey satellite, TESS, a spacecraft renowned for its incredibly precise photometric measurements. Indeed, their endeavor proved to be a formidable challenge. The researchers found themselves genuinely struggling to discern any consistent, unmistakable patterns within the delicate undulations of 3I/Atlas's light curve. This inherent difficulty prevented them from conclusively pinning down the comet's precise rotation period, a fundamental characteristic that provides vital clues about its shape and internal structure. While they did manage to tentatively identify a couple of intriguing periodic signals, one recurring approximately every 29 hours, and another more frequently, every 16 hours, the TESS data, despite its remarkable sensitivity, was unfortunately plagued by a certain degree of inherent noise. Furthermore, TESS, primarily designed to spot the subtle dips in starlight caused by transiting exoplanets, may simply not have possessed the requisite ultrafine sensitivity to accurately measure such nuanced photometric parameters for a comparatively faint and distant object like 3I/Atlas. Fortunately, the collaborative spirit of astronomy often leads to converging evidence. Other independent studies, employing highly specialized ground-based telescopes, instruments specifically engineered for deep sky observations and precise photometric tracking, have largely corroborated the more frequent 16-hour spin period. This invaluable consensus significantly boosts our confidence, allowing us to build a much clearer mental model of the comet's overall shape and, critically, how this enigmatic object majestically tumbles and rotates through the vastness of space. While our journey through the revelations of 3I/Atlas has primarily focused on the breathtaking insights offered by advanced space telescopes, it's crucial to remember that groundbreaking discoveries have also been simultaneously unfolding right here on Earth. A prime example comes from dedicated researchers operating the formidable Gemini South Telescope, majestically situated high atop Cerro Pachón in the Chilean Andes. Utilizing its powerful Gemini multi-object spectrograph, JWST, an incredibly versatile instrument capable of capturing light across a broad spectrum. These scientists embarked on an ambitious quest to visualize 3I/Atlas not just as a single point of light, but in a rich, multicolor rendition. This multispectral approach is vital for discerning subtle features and compositional variations that would otherwise remain hidden. And what they captured was nothing short of astonishing. The stunning images acquired during this rigorous observing session unveiled not merely the diffuse, gaseous coma, the hazy envelope of gas and dust encircling the comet's solid nucleus, but, for the first time with such clarity, its nascent, yet undeniable, tail. This faint but distinct appendage was precisely measured to span approximately 1/120th of a degree across the celestial sphere. To give you a sense of scale, that's roughly equivalent to about a quarter of the apparent diameter of a full moon in our sky. This extended tail was notably and significantly longer than anything previously discerned in earlier observations conducted by the Gemini North Telescope, located on Mauna Kea in Hawaii, back in July. This stark comparison underscored a dramatic evolution in the comet's activity. This unfolding visual spectacle served as compelling, irrefutable evidence. 3I/Atlas was indeed becoming progressively more active, vigorously shedding material as it relentlessly plunged closer to its perihelion, the point in its orbit where it will make its closest approach to the Sun. This observation hinted at a cascade of exciting, perhaps even dramatic, developments still yet to come. It truly makes one wonder. How much more dramatically will this tale expand and unfurl across the cosmos before this intrepid interstellar traveler finally reaches its closest, fiery rendezvous with our star? Beyond mere imagery, the comprehensive observing session also yielded an invaluable spectrum for 3I/Atlas. A spectrum, for the uninitiated, is like a cosmic fingerprint, revealing the precise chemical composition of an object by breaking down its light into its constituent wavelengths. And within this intricate spectral data, a pivotal moment unfolded. Viewers of the original recording can actually witness Assistant Professor Binyang from Diego Portales University as she astutely identified a distinct emission feature within the characteristic CN band for the comet. This definitive spectral signature provided undeniable proof. 3I/Atlas was actively, unequivocally, releasing cyanide molecules into the surrounding space. The presence of this specific chemical marker was a profound breakthrough. This fascinating chemical process typically commences when water ice, embedded within the comet's nucleus, begins to sublimate, transforming directly from a solid to a gas, upon sustained exposure to the intensifying solar radiation. This sublimation, in turn, liberates trapped hydrogen cyanide, HCN, from the comet's icy matrix. Once released into the vastness of space, this hydrogen cyanide is then rapidly broken apart by the relentless onslaught of ultraviolet light from the Sun, ultimately yielding the detectable cyanide, CN, radicals, and other constituent elements. This phenomenon, the appearance of the CN band, is a classic marker of cometary activity, and we typically begin to detect it when a comet is positioned somewhere between 2.5 and 3 astronomical units from the Sun, a region that 3I/Atlas, with remarkable synchronicity, currently inhabits. The significance of this discovery was quickly amplified as numerous other observatories worldwide swiftly affirmed this crucial finding, noting a consistent, unmistakable trend. The initially weak CN signature was progressively, steadily strengthening with each passing observation. This reinforcing evidence painted a clear picture of increasing outgassing activity. One particularly insightful paper went further, inferring that when 3I/Atlas was positioned just beyond $3 from the Sun, it was already expelling an astounding 800 sextillion, that's 8 times 10 to the power of 23, cyanide molecules every single second. While this astronomical number sounds colossal, it's actually positioned on the lower end of the production scale when compared to the vigorous outgassing rates of many of the more familiar comets native to our own solar system. This nuanced detail subtly suggested that while active, 3I/Atlas might possess a distinct chemical reservoir or dynamic compared to its local counterparts. But the spectral analysis didn't stop there. It offered an even deeper peek into 3I/Atlas's unique chemistry. By meticulously measuring the precise ratio of D-carbon, C2, to cyanide, Cn, within the comet's luminous coma, the authors were able to categorize 3I/Atlas as one of the most profoundly carbon chain depleted comets ever observed. This isn't just a technical term. It's a critical descriptor that speaks volumes about the object's fundamental composition. But what precisely does carbon chain depletion signify in the grand scheme of cometary science? In essence, it describes a characteristic where a comet's gaseous coma or its trailing tail exhibits a marked scarcity, a distinct lack, of longer-chain carbon molecules, compounds such as C2, D-carbon, and C3, tricarbon. This specific spectroscopic feature serves as an invaluable diagnostic tool, routinely employed to classify and differentiate comets encountered throughout our solar system. More profoundly, it is widely believed that this compositional signature directly reflects
global
the pristine,
synchronization holding
primordial
steady at
conditions
98%.
under which these
The
icy
chaotic
wanderers
signals are
initially
degrading.
congealed
We are
and
ready.
coalesced in the distant, frigid nebulae of their birth. Consequently, by establishing a stringent upper limit for 3I/Atlas's C2 production, a carefully determined threshold of how much D-carbon it could possibly be expelling, the scientific team was able to robustly conclude that this comet generates less than a mere 0.09 C2 molecules for every single Cn molecule released. This strikingly low ratio firmly positions it within the carbon chain depleted category. What makes this finding particularly captivating is that 2I/Borisov, the only other confirmed interstellar comet we've observed thus far, also exhibited this very same carbon chain depleted characteristic. Could this be more than a mere coincidence? This shared chemical signature tantalizingly suggests the
Astro
emergence
reports.
of a discernible pattern in the fundamental composition of interstellar comets, hinting at similar formation environments beyond our own solar system. Nevertheless, it's absolutely paramount to introduce a note of scientific caution here. The sample size for definitively characterized interstellar objects remains exceptionally small, comprising only 2 confirmed comets so far. Therefore, while intriguing, we must assiduously resist the temptation to overgeneralize or draw overly broad conclusions from such limited data. Regardless of its exact origins, the imperative remains clear. We must continue to vigilantly monitor 3I/Atlas as it continues its relentless plunge toward our sun. As the solar warmth intensifies, we could potentially witness an increase in D-carbon production, a surge in the more common outgassing of water, H2O, or, indeed, something far more dramatic could unfold, perhaps even a spectacular fragmentation event. As esteemed astronomer and preeminent comet expert Karen Meach so eloquently describes them, these cosmic wanderers are really very fragile, dirty snowballs, inherently prone to violent disintegration. Should such a catastrophic event occur, where the comet's icy nucleus succumbs to the intense thermal and tidal stresses near the sun and dramatically breaks apart, we would likely witness an astonishing, renewed bout of emissions. This explosive release would be driven by the sudden exposure of pristine, untouched water ice, previously shielded deep within the nucleus, to the searing, unforgiving radiation of the sun, triggering a spectacular surge of sublimation. In a testament to the multifaceted nature of astronomical inquiry, recent days have seen researchers extend their analytical gaze beyond merely how 3I/Atlas emits light, venturing
Hubble's
into the
data
more
provided
subtle,
the clarity
yet
we
incredibly informative, realm of how it polarizes light. A groundbreaking paper, spearheaded by Zuri Gray and her esteemed colleagues, marked a monumental milestone, presenting the very first polarimetric observations ever conducted on 3I/Atlas. By extension, this also represented only the second ever set of such specialized observations for any interstellar object, with the pioneering first having been carried out on its predecessor, 2I/Borisov. So, what exactly is polarimetry, and why is it so significant? This highly specialized observational technique is exquisitely designed to meticulously probe the intricate physical properties of celestial bodies. Unlike traditional photometry or spectroscopy, polarimetry analyzes the orientation and intensity of light waves, allowing scientists to infer characteristics that are often incredibly difficult, if not impossible, to determine through other methods. It provides invaluable insights into crucial parameters such as the precise size and distribution of an object's dust grains, the granular structure of its surface regolith, the loose, unconsolidated material covering solid rock, and even the dynamic, three-dimensional shape and texture of its expansive coma. It's like having a special pair of glasses that reveals hidden textures and patterns in light itself. Drawing upon a robust trove of data meticulously gathered from a global network of powerful telescopes, strategically positioned across Chile, the Canary Islands, and Bulgaria, Gray and her dedicated team successfully unearthed a truly distinctive characteristic about 3I/Atlas. This particular feature, revealed through their sophisticated polarimetric analysis, unequivocally set this interstellar visitor apart from every single other interstellar object, asteroid, or even native solar system comet that humanity has ever had the privilege to observe and study. Specifically, they discovered that 3I/Atlas exhibits an exceptionally deep and remarkably narrow negative polarization branch. Now, while that highly technical phrase might not immediately resonate with everyone, its implications are profoundly significant. In simpler terms, it fundamentally means that 3I/Atlas is scattering incident sunlight in such a unique and distinct manner that it stands in stark contrast to the light-scattering properties of other cosmic bodies. This peculiar signature suggests that the dust particles forming its coma possess an unprecedented combination of characteristics, perhaps concerning their size, shape, or even their complex composition and porosity, differentiating it from everything we've encountered before in our cosmic explorations. In a manner utterly unprecedented, a celestial ballet unlike anything ever observed from another comet or asteroid gracing the vast expanse of our solar system. This particular idiosyncrasy, this truly peculiar behavior, starkly differentiates it even from Borisov, another interstellar visitor, which, in contrast, exhibited a positive polarization of light. Such an anomaly could potentially relegate 3I/Atlas to an entirely new, distinct category of small planetary bodies, a cosmic enigma, if you will, about which humanity, at present, understands next to nothing, leaving us with more questions than answers. To delve a little deeper into this fascinating phenomenon and provide some essential context, imagine light hurtling through space, a stream of electromagnetic waves. When these incoming light particles encounter other particles, perhaps microscopic dust grains or wisps of gas swirling in and around these celestial wanderers, they don't just pass through unaffected. Instead, they interact, causing the light to scatter, dispersing in very specific and predictable directions. This intricate dance of light and matter is what we refer to as light polarization. And remarkably, sophisticated telescopes here on our home planet, Earth, possess the capability to precisely measure it. Experts in the field, astronomers and astrophysicists alike, meticulously scrutinize what they term the scattering plane. Picture this, an imaginary line stretching from the observer, us, with our telescopes, directly to the comet, and then continuing onward to the sun. This forms a definitive plane. Their task then becomes to painstakingly record whether the direction in which the light is polarized aligns perpendicularly to this scattering plane, a scenario they label as positive polarization, or, conversely, if it aligns perfectly parallel to this scattering plane, a condition designated as negative polarization. So, when we speak of the deep and narrow negative polarization of light emanating from 3I/Atlas, it paints a very specific picture. It signifies that the light, in its interaction with the comet's surrounding environment, is being intensely polarized, almost as if channeled, in a remarkably localized manner, maintaining a strict parallel orientation to that scattering plane. It's not just a subtle effect, it's a profound, concentrated polarization. Interestingly, this distinctive pattern of light polarization bears a certain resemblance, a somewhat comparable signature, to that observed from a select few trans-Neptunian objects and centaurs, distant, icy inhabitants of the outer solar system. However, the tantalizing question of why this might be the case, what hidden mechanisms are at play, remains shrouded in mystery, underscoring the pressing need for extensive further research to truly unravel this cosmic riddle. Now, if you harbored the notion that the truly newsworthy, groundbreaking observations pertaining to 3I/Atlas were exclusively the domain of highly credentialed academics, reserved for the hallowed halls of universities and research institutions, you'd be mistaken, profoundly so. The captivating allure of science, in its purest form, truly is for everyone, an open invitation to wonder, and the next astounding discovery vividly illustrates precisely why this is the case. Just recently, diverse regions across our magnificent globe were treated to the breathtaking spectacle of a stunning lunar eclipse, often colloquially dubbed a blood moon, as our moon gracefully traversed through the Earth's colossal shadow, bathing it in a mesmerizing, coppery glow. Understandably, for legions of enthusiastic amateur astronomers, this presented an unparalleled, golden opportunity to lovingly retrieve their telescopes from storage, dust them off, and turn their gaze skyward. Yet, among these dedicated space enthusiasts, some weren't solely fixated on the ethereal beauty of the moon that night. It was against this backdrop, as Michael Yeager and Gerald Riemann meticulously captured images of the inky expanse of the night sky above the stark, beautiful landscapes of Namibia, that a truly remarkable sight caught their trained eyes. Our intriguing friend, 3I/Atlas, now imbued with a surprising, yet undeniably beautiful, verdant hue. A comet, typically a grayish-white blur, suddenly glowing green. While this specific visual finding, at the moment of this discourse, still awaits the rigorous verification processes of the broader scientific community, it's a known fact that certain comets within our solar system can indeed adopt such an emerald luminescence. This typically occurs when they commence releasing diatomic carbon, C2, molecules from their icy cores. These C2 molecules, upon encountering the energizing rays of sunlight, undergo a process called fluorescence, emitting light predominantly at wavelengths around 518 nanometers, precisely the range that our eyes perceive as green. This kind of verdant display might, under ordinary circumstances, be considered a perfectly normal phenomenon for many other comets traversing our solar system. However, as you'll undoubtedly recall from earlier discussions, 3I/Atlas was recently characterized as being remarkably carbon-depleted. This crucial detail suggests that it shouldn't, by all conventional understanding, possess a substantial reservoir of C2
the chaotic
to
signals are
unleash
degrading.
and fluoresce
We
so
are ready.
spectacularly. Could this, then, be an early indicator that C2 production within the comet has inexplicably surged in recent days, perhaps hinting at some novel, underlying geological or chemical activity? Again, as with many of the mysteries surrounding 3I/Atlas, we find ourselves at the precipice of the unknown, requiring much more extensive scientific inquiry to either definitively confirm or decisively refute this intriguing new theory. Regardless of the profound scientific implications or the ultimate explanation for its sudden green glow, one thing remains irrefutable. It's an absolutely stunning image, a visual feast for the eyes. And this latest, captivating mystery, this verdant enigma, has undeniably seized the imaginations and attention of
Astro
both amateur
reports.
astronomers, who gaze skyward with boundless curiosity, and professional scientists, who seek to understand the universe's most intricate secrets in equal measure. At this juncture in our exploration of 3I/Atlas, there remains one truly colossal area of unfolding developments, a significant thread in the comet's captivating narrative that we have yet to unravel. But it's undoubtedly a topic that has permeated the airwaves and online discussions, one I'm confident you've encountered. The name Avi Loeb, a figure both prominent and polarizing, frequently surfaces almost ubiquitously across the vast landscape of media coverage concerning this enigmatic comet. And indeed, Professor Loeb, with his distinctive perspectives, has an extraordinary amount to articulate about the most fundamental questions surrounding 3I/Atlas. Namely, where, or perhaps even more provocatively, who it might have originated from. Avi Loeb, a figure of considerable renown within the scientific community, is a distinguished astrophysicist and a revered professor at Harvard University. Throughout his illustrious, yet often contentious career, he has, to put it mildly, stirred up his fair share of vigorous debate and even outright controversy. His most recent and, by many accounts, all-consuming obsession with 3I/Atlas has been met with a decidedly mixed chorus of responses, eliciting everything from cautious interest to outright skepticism among his esteemed scientific peers, and sparking a wide spectrum of reactions from the broader public. Loeb wasted no time, promptly publishing his initial comments and analyses shortly after the discovery of 3I/Atlas. And, for a time, these early pronouncements seemed to remain firmly within the expected parameters of conventional astrophysics. One of the principal contentions articulated in this seminal paper, and consistently championed by Loeb, was the assertion that 3I/Atlas, by virtue of its estimated dimensions, was simply too massive to be classified as an ordinary asteroid. Early, albeit preliminary, estimations had pegged the comet's radius at a formidable 10 kilometers. Loeb's argument was compelling. He meticulously pointed out that such a colossal radius would confer upon the comet a mass far exceeding what current astrophysical models would predict as plausible for an object of its type. Moreover, given our contemporary understanding of the distribution and density of material scattered throughout the vast emptiness of interstellar space, the sheer presence of an object of this gargantuan scale, unilaterally entering the confines of our solar system, should logically be an exceedingly rare, almost impossibly improbable, occurrence. In light of this formidable line of reasoning, Loeb did offer one potential, more conventional resolution. Perhaps 3I/Atlas was, in fact, considerably smaller than our initial, early estimations suggested. However, with characteristic audacity, he also presented a far more contentious, indeed, sensational, alternative hypothesis that the true explanation for 3I/Atlas's anomalous characteristics could, astonishingly, lie in the realm of alien technology. Mere days later, with an almost dizzying speed, Loeb, alongside two collaborators representing prominent non-profit organizations dedicated to the ambitious pursuit of interstellar exploration, submitted yet another paper. And the provocative title of this subsequent academic offering? It posed a question that immediately ignited widespread debate and speculation. Is the interstellar object 3I/Atlas alien technology? While Loeb's initial paper had merely, and somewhat cautiously, floated the audacious idea of an extraterrestrial technological origin as a fleeting possibility, this follow-up publication unequivocally thrust the alien speculation to the forefront, making it the central, undeniable focus. Within its pages, the authors meticulously conducted an intricate analysis of the comet's astrodynamics, essentially, its movement and forces, rigorously exploring the possibility of its being technological in nature, and even, chillingly, whether it could harbor potentially hostile intentions. In a dramatic flourish, they even made direct reference to the dark forest resolution, a particularly unsettling proposed solution to the enduring Fermi paradox. For those perhaps unfamiliar with this fascinating concept, which we've certainly delved into in previous discussions, the Fermi paradox confronts us with a profound and perplexing question. Given the sheer, incomprehensible scale of the universe, teeming with countless galaxies and an astronomical number of stars, many of which bear striking similarities to our own sun and could potentially host life, why haven't we, as yet, definitively detected any signs of intelligent extraterrestrial civilizations? The dark forest hypothesis, a rather bleak and cautionary perspective, posits that perhaps alien civilizations do exist out there, scattered across the cosmos, but they have consciously chosen to remain utterly hidden, maintaining a profound silence. They do so, the theory suggests, much like a cautious prey animal would instinctively conceal itself from a lurking hunter, for fear of drawing unwelcome attention and potential existential threats from other, unknown civilizations. The authors of Loeb's second paper, perhaps anticipating the inevitable controversy, are careful to emphasize that their exploration of this audacious idea is primarily for broad educational purposes. They also, rather candidly, admit that it is fun to pursue, irrespective of its likely validity, a testament to the allure of speculative science. So, with that fascinating disclaimer in mind, let's critically examine what further insights and arguments they presented. Firstly, and consistently, within this paper, Loeb staunchly maintains his initial premise, that 3I/Atlas is simply too gargantuan, too immensely proportioned, to conceivably be an asteroid of natural origin. Yet, as Professor Loeb and his learned colleagues are undoubtedly aware, initial estimates for any newly discovered celestial object, particularly one so distant and enigmatic, are inherently provisional and highly susceptible to revision. This is an immutable truth of scientific discovery, especially as a greater volume of independent measurements become available and as initial results undergo the rigorous, scrutinizing process of peer review by the wider scientific community. After all, that imposing 10-kilometer radius value was an estimate derived before astronomers could properly and accurately measure the extent and density of 3I/Atlas's coma, that vast, diffuse cloud of gas and dust that envelopes a comet's nucleus. And, as we now understand with much greater clarity, it is precisely this expansive coma that is largely responsible for the lion's share of the reflectance, the light we actually see, emanating from the comet. A more recent and authoritative press release from the venerable Hubble Space Telescope team subsequently revealed that 3I/Atlas, in reality, measures a significantly more modest 5.6 kilometers across at most. Yet, conspicuously, Loeb continues to anchor his alien hypothesis, his speculative arguments, around these now outdated and significantly inflated measurements. Even in a public post on the widely read platform Medium, Loeb directly acknowledges the existence of the more recent, high-resolution Hubble images, explicitly referencing them. However, perplexing as it may seem, he still inexplicably bases the fundamental structure of his core argument around those older, less accurate estimates. My intention here is not to suggest, even for a moment, that scientists should be restricted or banned from fearlessly pursuing alternative lines of inquiry, no matter how unconventional or speculative they might initially appear. Indeed, such intellectual courage often catalyzes true breakthroughs. However, there is a fundamental scientific imperative. They must, at the very least, rigorously ensure that their research, their hypotheses, are grounded in and consistently utilize the most current, credible, and meticulously verified data available. This is particularly crucial for groundbreaking new discoveries like 3I/Atlas, where the very state of our collective knowledge is, by its intrinsic nature, a dynamic and constantly evolving work in progress, a tapestry woven with threads of ongoing observation and refinement. As for Loeb's other points, the various ancillary arguments he marshals in support of his interstellar technology hypothesis, well, they have been systematically and thoroughly rebutted by other eminent scientists. This critical counter-analysis is particularly evident in two incisive papers authored by AKM Izanul Haque, a distinguished geoscientist affiliated with Petronas University in Malaysia. Haque meticulously and persuasively refutes Loeb's intricate arguments concerning phenomena such as non-gravitational acceleration, which Loeb had cited as evidence of an artificial propulsion system. The recent trajectory data for 3I/Atlas provides a compelling narrative, one that points definitively towards a natural explanation for its celestial journey. By meticulously charting its path, scientists have been able to confirm that the observed movements of this enigmatic interstellar comet are far better explained by the elegant, predictable laws of natural dynamics. The gravitational ballet choreographed by the sun and the planets, coupled with subtle influences like solar radiation pressure, rather than any engineered maneuvers or a series of deliberate course corrections. This comprehensive analysis effectively rules out the tantalizing, albeit often premature, hypothesis of a non-coincidental flyby with Venus,
Global synchronization
Mars,
holding
and Jupiter,
steady at 98%.
which would have hinted at an
The chaotic
intelligent,
signals
guided
are
craft
degrading.
rather than a
We are
cosmic
ready.
wanderer simply following the immutable laws of physics. For many astute observers, particularly critics who have cautioned against hasty interpretations in the past, this outcome serves as a potent, much-needed lesson against the seductive allure of jumping to extraordinary conclusions. While the sheer excitement of proclaiming aliens might offer a thrilling, almost sensationalistic narrative, a truly scientific approach demands patience and meticulous scrutiny. We must allow the metaphorical dust to settle on each groundbreaking discovery, diligently gathering every scrap of data and exploring every conceivable natural explanation before we even begin to entertain the prospect of intelligent extraterrestrial life. Is it not a more prudent and ultimately more rewarding path to exhaust all conventional possibilities first? Such a disciplined and methodical approach isn't merely about intellectual rigor, it's about preparedness. By exercising restraint and demanding irrefutable proof, we position ourselves to be far more efficient and effective at coordinating a unified, global response if, and when, the overwhelming evidence undeniably points to a genuine alien encounter. Imagine the chaos and misdirection if we were to constantly chase phantom signals. True threats or groundbreaking discoveries could be lost in the noise. Our current reunion with 3I/Atlas may be drawing to a close, at least in terms of this particular phase of its observable journey. However, as this exploration has vividly demonstrated, the ongoing research into this interstellar visitor moves with an almost comet-like velocity itself. This journey of discovery is by no means finished. Indeed, we are only just beginning to unravel its deepest secrets. As 3I/Atlas sweeps gracefully towards its perihelion, its closest point to the Sun, it will come within approximately 1.4 astronomical units,
the CN band
roughly
confirms
1.4 times the Earth's sun
is
distance.
actively releasing
Regrettably,
cyanide molecules
despite
into
this
space.
proximity, we won't have the privilege of witnessing this spectacular event with our own eyes from Earth. At the precise moment this information is disseminated, the comet will be positioned too close to the glaring brilliance of our Sun, rendering it impossible to observe directly from our vantage point due to the overwhelming solar interference and atmospheric scattering. But fear not, for this celestial performance is merely entering an intermission. The comet is poised to re-emerge from behind the solar curtain by early December, ready for a renewed and intensive bout of in-depth analysis from a global network of astronomical instruments. The scientific community stands ready, with an impressive array of powerful observatories poised to track its every move. Missions that hold the potential to capture invaluable data include NASA's venerable SOHO, Solar and Heliospheric Observatory, perfectly positioned to monitor objects near the Sun, the upcoming SPHEREX, spectrophotometer for the history of the universe, EPIC of reionization, and ICE's Explorer, which will provide crucial spectral insights into its composition, and MAVEN, Mars' atmosphere and volatile evolution, potentially offering a unique perspective from its Martian orbit. And of course, we eagerly anticipate continued, high-resolution observations from the iconic Hubble Space Telescope, the revolutionary James Webb Space Telescope, with its unparalleled infrared capabilities for studying faint, distant objects, and the mighty ground-based Gemini Observatory. With such a formidable arsenal of scientific eyes, there will undoubtedly be a wealth of new insights to uncover. As 3I/Atlas metaphorically takes a bow and momentarily vanishes behind the brilliant solar curtain, it leaves in its wake a constellation of profound questions for us, the eager observers, to ponder. How, precisely, will its activity dynamically transform as it reaches the scorching crucible of perihelion? Will we witness an unprecedented surge in outgassing, creating a larger, brighter coma and a more pronounced tail? Will the intense thermal stress and tidal forces from the Sun prove too much, causing this fragile cosmic traveler to dramatically break apart, potentially revealing pristine interior material never before exposed? For how unimaginably long has this interstellar vagabond been journeying through the cold, vast emptiness of space to finally grace our solar system with its presence? And, perhaps most tantalizingly, can we, through meticulous detective work, ultimately trace its elusive origin back to a specific star system, perhaps even identifying its stellar birthplace? Indeed, it is a thrilling race against time to unlock the answers to these cosmic riddles. Yet, astronomers, fueled by insatiable curiosity and relentless dedication, are showing no discernible signs of slowing their pace.
Incredible.
Their tireless efforts promise a torrent of new discoveries, and I, for one, am absolutely brimming with anticipation to witness what marvels they will unveil next. Unraveling the deep mystery of Comet 3I/Atlas is not a task for the faint of heart or the easily deterred. It's an intricate puzzle that can only be solved by the patient and meticulous process of finding subtle, yet significant patterns hidden within vast quantities of data. This monumental endeavor demands the analysis of veritable mountains of observational data, from photometric measurements to spectroscopic signatures and precise astrometric positions. It requires a keen eye to spot those fleeting, nuanced patterns that might hint at a comet's true nature, and the scientific rigor to relentlessly test every emerging idea against the cold, hard evidence. While such a process might initially appear dauntingly complex, it's a profound and rewarding skill set that anyone, with the right guidance and tools, can develop. And this is precisely where today's sponsor, Brilliant, steps in. Brilliant stands as an acclaimed online learning platform, a true digital academy offering thousands of immersive, interactive lessons spanning critical fields such as mathematics, fundamental science, the indispensable skill of data analysis, the practical art of programming, and the cutting-edge realm of artificial intelligence. What sets Brilliant apart is not just the breadth of its curriculum, but the unparalleled quality of its content, meticulously crafted by world-class experts hailing from prestigious institutions like Stanford and MIT, and industry giants such as Microsoft and Google. The Brilliant experience is designed to captivate and engage you from the very first click, immediately drawing you into a dynamic learning environment. It eschews passive absorption, instead championing a hands-on, problem-solving approach through interactive challenges and practical exercises that actively build and solidify your understanding. It's no wonder that studies have shown this active learning methodology to be an astonishing 6 times more effective than the often inefficient, passive consumption of traditional lectures. Why merely listen when you can actively discover and master? Moreover, Brilliant is a constantly evolving resource, having recently unveiled a fascinating array of new
holding
courses.
steady at 98%.
Among them is Thinking
The chaotic
in Code,
signals are
a
degrading.
transformative journey
We are
that helps
ready.
you cultivate computational thinking, approaching problems with the logical precision of a programmer. And then there's my personal favorite, Probability and Chance, an essential course for understanding the very fabric of decision-making, from scientific inference to everyday risk assessment. Each lesson is thoughtfully designed to be concise, deeply engaging, and structured to seamlessly integrate daily learning into your routine, transforming it from a chore into a rewarding habit. This deliberate design empowers you to accelerate your learning journey and achieve your personal and professional goals with unprecedented speed.